Welcome to another problem session. So this is an interesting problem. It's coming from Klepner and Kolenko, kind of modified a little bit. Okay, so what do we have here? We have a rocket which has a cylindrical body and a conical nose. Okay, and it's traveling through this cloud. So this is a cloud. And there are numerous particles here. So this is the particle density, which is number of particles per unit volume. Okay. Each of the particle has little mass m, and the rocket mass is big M. And as it's going at t equal to 0, the speed in the nose direction is v0. And the cloud is, if I'm over here, so this is with respect to this frame. So this is the inertial frame. So this v0 is with respect to this frame, and the cloud is at rest. V cloud equals 0 with respect to, let's call it frame S, inertial frame S. Okay. And we're supposed to find the velocity at some time, and velocity t equals 0 is given. So basically we need to figure out change in velocity with time. That means we need to work with F equals ma at some level, right? And things that we have to assume is these particles are bouncing off elastically, and that this nose angle, half angle, 45 degrees is chosen. It will simplify calculation. All right. So let's draw a little bit of picture of what will happen at the nose. So 45 degree will look like something like that. So this is the nose, and say a particle comes in. So now is in the frame of the rocket. So rocket frame, okay. In this frame, rocket is at rest, and the cloud particle is moving towards the rocket. So this is little m moving to the rocket. So in this frame, you can clearly see that after this, if you look at the bounce off business, it's going to, if this is 45 degrees, then this is 45 degrees, and so it's going to bounce up straight up. So this particle comes in with v, say at some time t is v. Initially it will be 0, and then some other time v. It's going to come out because elastic, this will have to be same as that. Is bouncing up elastically, is holding on to its kinetic energy, right? So speed is v, it's going to, and the direction change already known. Okay, so you'll have exactly same vector diagram with respect to even this frame, right? So in this frame, what will happen is you are going to you're going to see that this change in momentum, will reflect the change in momentum of this guy, right? So momentum of the rocket plus momentum of the particles should should be constant. So if this is in change momentum of the particle, then you have to say what's the change momentum of that guy. Now, if you look at another particle, which is situated just like above there, and we're supposed to assume this is almost continuous. There's so many of them that's almost continuous cloud, See, the second particle like this is going to come down like that. So that for every particle like this, there will be a second particle like this, just from the symmetric situation. So this momentum change, this momentum change, they will cancel each other out, right? So the only momentum change that is like momentum coming in, there's no momentum in that direction. So this momentum disappeared. This new momentum appeared, but that got cancelled by this momentum over here. So if this was the y direction, I don't need to worry about y direction, just worry about x direction. So let's see how many particles. So you had the rocket and you have, so these particles, you can see that all the particles that are say at some time, at some instant t, which may not be that one, okay, some instant, arbitrary instant t, this rocket is going with some velocity v. So you can see that, let's look at this. So this, if this distance is v delta t, so what's going to happen very next delta t is these particles in this volume will have stricken this, will strike this, right? Because if this is here, then the nose will go all the way there, and then all these particles will have hit that. So we need to figure out how many particles are here, and its momentum is what the change of momentum will be. So the number of particles here should be equal to the volume of this, which is, if this is the area of cross section, so this is pi r square. So this, we call it area, projected area. So projected area is pi r square. So a projected v delta t, so that's the volume, and it says that n is the number of particles per unit volume. So this is going to be the number of particles there. So this is pi r square n v delta t. So between t to t plus delta t, this many particles will hit. So we're just examining this. And mass of each particle is m. So, and each particle has mass little m, and velocity in the x direction is v. So we're just all looking at x direction here, whether in this frame x direction or this frame x direction, we're just looking at x direction. So x direction, when this guy hits, is going to be is going to provide a change in momentum in the negative side. It has a negative momentum, and then later on didn't have any momentum. So the momentum change for the cloud particle will be negative. So momentum change of this guy will be just exactly opposite, right? So delta p, let's call it p, delta px of this guy, and we'll make sure we have the negative sign later on, okay? So right now we're just going to write down what we expect. Expect these particles, so this is the number. So we want the number and we want the mass times v. And so this should be a negative number here, and it's going to be minus, number will be pi r square n v delta t times m times v. So there are two factors of v. So, and the rest of them is, all of them are constant except this guy. So let's write down minus b v square delta t, where the b is standing for pi r square n m. So that's the b. All right, so just all the constant together. So on the rockets, this is a change in momentum of rocket. So divided by delta t, so delta px over delta t equals to minus v square. Now this should equal this will be the force applied by the hitting particles, right? So this should equal to f x, and this should equal to m a x. This should equal to m dvx, big M, this time rocket's mass, big M dv dx. And this is same as this for us because we're looking at the positive that way. So if you want to call this guy vx, that will be fine. Or this, call this v, so we just write down m dv dt. So all the x components, just extra x, no need to write that. So you have a dv over v square equals minus b over m times dt. So you know by now that eventually f equals ma is a differential equation, and you're going to have to solve something like this. Now the way we've separated t, there's nothing v here. We've separated v, and there's no t on this side. So this is called separated, and then we just have to integrate it, and you go 0 to t, and when it's 0, this side it was v0. When it's t, we are calling it v. So that just becomes v to the power minus 2 plus 1 divided by minus 2 plus 1. This is v n, so b, I don't know, I don't know how you do this integration, yourself. I just actually I did a little extra step here just to show that this guy is basically v to the power minus 2, and just add 1, and then the whole thing comes down here, and v equals to minus b over m, and just t, because of 0 you don't have another term here. Okay, so this is just minus 1 over v, minus plus 1 over v0 is equal to minus b over mt. Now it's a matter of doing this algebra. Bring these guys on the other side, this on the other side, or just multiply by minus everywhere. I don't know. Again, if I multiplied minus, this becomes plus, and this becomes minus, and this becomes plus. Then I bring this guy on the other side. So 1 over v equals to 1 over v0 plus b over mt. And so you can see I can do v0 m, and this is capital M, this m plus b v0 t, and so v equals to v0 m over m plus b0 t. You can divide the numerator and denominator by m. So this whole thing by m and this by m, then it just becomes v0 and 1 plus b over m v0t. So any of this, all of these are answers, okay? So this is a pretty interesting problem. You can just plug in some reasonable numbers to see if it makes sense to you. All right. So I think I'll leave it that. This is a problem that kind of shows up in tests quite a bit, actually, in some type of situation. Sometimes you will say, okay, not just V, you'll be asked, an extension I can just immediately see is now it is slowing down, right? So you'll need your rocket to have thrust to get past the cloud, right? So if the rocket is to maintain the same as V0, the question will be, if this rocket is to maintain V0, keep going at V0, what kind of thrust you will need to maintain it at V0? Okay, so that's a question for you. What thrust will be needed to maintain cruise speed of V0? Okay. The question will be, okay, how much fuel will be required if they give you some kind of data about if you burn this much fuel, you get this much energy. So what kind of fuel how much fuel you'll be burning in, say, in 10 seconds and things like that. So all of those things are extensions of this, but basic idea is very similar. It all begins with actually understanding like this step, what happened in an incremental unit of time. So if you understand the logics I try to give you, I think you can pretty much handle other problems like this. All right. So with that, I will have a request a little bit, just that subscribe to this channel. So that's one request. Another one is that you can tell your friends. You can tell your teacher that, here is a channel that actually solves interesting physics problems and goes in detail about a strategy of how to approach these problems. And so I'll see you in the next video. Bye.